Okay, so as I was talking about, we have waves, and we also have frequency associated with it. We saw some equations. C is equal to the wavelength times the frequency. C being the speed of light, which is here 2.99979, I think, times 10 to the 8 meters per second. I feel like I got that backwards there. There you go. We have our wavelength, which is usually in meters. We have our frequency, which is reciprocal seconds, are again a hertz, which is a one-to-one relationship between those two. And we also talked about sort of energy associated with these waves. And remember that if you have sort of a small wavelength, you typically will have a high frequency, and you usually will have a higher energy sort of wave associated with it. If you have a kind of a longer wavelength, you will have usually a lower frequency and a lower energy associated with it. We calculated the energy as well for a photon of light. E is equal to h times the frequency. Energy being in joules, h being Planck's constant, 6.63 times 10 to the minus 34 joule times seconds. And obviously our frequency here in reciprocal seconds. Here the seconds will cancel, and that will leave you with joules that's over. We also talked about that you can use this equation with that one. And if you rearrange this equation, solve for the frequency, which is c divided by the wavelength, and then put that into this equation here, you get E is equal to hc divided by the wavelength. So that allows you to calculate the energy if you know the frequency of that photon of light. Also allows you to calculate the energy if you just know the wavelength. A reminder that the wavelength does need to be in meters in this because of the speed of light, so that everything cancels out correctly. So you can calculate the energy, or again, the frequency associated with a wavelength of light. Remember, we're really talking about all this in context to electrons transitioning from one energy level to the next. And obviously, as the electrons drop from a higher energy level to a lower energy level, energy needs to be given off in the form of a photon of light. Remember that that wavelength of that light coming off could fall somewhere in the electromagnetic spectrum that we also saw, where we had radio waves, microwaves, infrared, visible part of the spectrum, where we do see colors, X-rays and gamma rays, and also UV in there as well between those two. And it does not necessarily mean that it has to come off in a sort of visible part of the spectrum when we do see color. If the electron goes from, say, a lower energy level to a higher energy level, that is for the atom an endothermic process. Energy has to be put in, kind of like when you do a flame test. You put all that energy in, the electrons get excited, they go to a higher energy level. Eventually, as we talked about things in chemistry, you want to be in the lowest state of energy possible. So if the electrons are kind of going from a higher energy level to a lower, the atom will actually give off the energy, and it'll actually be exothermic in that case. And again, that is where we typically see an emission spectrum from the energy coming off as those electrons transfer. Any questions on any of that stuff that we talked about before? Also, a reminder again, they do want you to know H and the value of C, and those things are usually not given to you in problems, so they just kind of assume that you know you have those available to you to use for a calculation. So I think we ended on a calculation, so I think we did not do this one if I'm not mistaken. So let's do this one and see what you come up with. We're looking for the energy. We are given the frequency of 2.87 times 10 to the 14 reciprocal seconds. In this case, we got you just go right into our equation. Once again, never usually given to you, but a value that is a constant that you should always have, 6.63 times 10 to the minus 34 joules times second, which is Planck's constant. So really just got to plug it in here, and we will get... And in this particular case, our seconds will cancel each other out, leaving us just joules, which is good because that is an energy. And that is an energy of something. Let's see. 6.63. That is a. Looks like 1.90 times 10 to the minus 19 joules. Questions on that calculation? So you do need to know those two formulas there. Again, are E is equal to H times frequency, or C is equal to the wavelength times frequency. To be able to solve for energy, wavelength, or frequency, depending on what is given to you. Any questions? So as we've been talking about, essentially what we're sort of looking at here is that idea of electrons transitioning from one energy level to the next. Again, with the conservation of energy, they have to give off that energy as they again transmit from a higher energy level to a lower energy level. Remember that if it does fall in the visible part of the spectrum, we will see color. And even the color of light, as we also talked about, does have differences in terms of energy. So if you remember, red is like 700 nanometers in that range, which is a longer sort of wavelength than, say, by the purple, which is in the 400s. So a red color would imply lower energy coming off versus, say, something closer to the purple sort of color. That also, again, as we talked about, you can think about just how many energy levels perhaps an electron is transitioning. So if you had one that went all the way from the top to the bottom, that's probably going to give you something with a lot more energy, as it had to transfer through a lot of energy levels to get there, and also result, if it was in the visible part of the spectrum, more of a purple type color, as opposed to, again, if we just saw maybe an electron starting here and it just dropped to there. Again, not a tremendous amount of energy difference between those two energy levels, would probably give you something with a longer wavelength, maybe closer to sort of the red. Now, this brings us to, and we're talking a little bit about Bohr's theory of the atom, but one of the things that we talk about when we're talking about electrons transitioning from one energy level to the next is this idea of emission spectrum. And emission spectrum is usually what you get when those electrons are transitioning from a higher energy level to a lower energy level. Basically, the atom is giving off all this energy in the form of photon of light. And that emission spectrum, for example, if it falls in the visible part of the range, may result in kind of two different types of spectrums that we'll talk about that you can get. The way you would do this, for example, if you wanted to, is again, you can excite your sample and that will excite those electrons and give off those emissions. You could do that like you did before. Again, put it in the fire. That's definitely going to add a lot of energy to that. You could also use like an electrical discharge tube, kind of like neon lights, run electrical current through it, right? And it excites all of the atoms there and those electrons, and you see different colors. When we talk about sort of spectrums that we come across, sometimes we get different types of spectrums that develop. So we do see, for example, if you put a piece of iron in a fire, it's going to glow, which gives you that visible part of the spectrum. But again, remember there are different parts like UV, infrared, gamma, X-rays. For example, the warmth would be from like the infrared part of the spectrum, maybe not a color or anything like that. So a common feature of the emission spectrum of the sun and heating solids is it gives more of what's considered a continuous spectrum. And if you remember last time, we talked about sort of the idea of quantized energy, which is kind of like that staircase example going up and down stairs where you're either at one energy level or the next. When you think about sort of a continuous spectrum like you see with the sun and heated metals, it's more like if you want to think about like a ramp, if you will. If you were walking up a ramp, you essentially could stop anywhere along the way on the ramp and you would have like no problem. Unlike stairs, which is more quantized version of energy, where you got to be either on this step, or that step, or otherwise you're going to fall. So what happens usually in the continuous spectrum is because you could really have transitions that occur all the way through there, you can get a spectrum that's basically everything coming out at once, like so all the colors of the rainbow pretty much coming out at once. So as opposed to here, which is more of a quantized version, as we will see, you'll get these really distinct sort of spectrum that occurs, which is referred to as a line spectrum. And we'll see these distinct lines at specific wavelengths rather than just everything coming out at once. Now, as I just mentioned a second ago, we do see a more line spectrum. And different than that is if you looked at it, through say like a prism and it separated out everything, you would see these specific lines that would have obviously specific colors if they were in the part of the visible part of the spectrum, and they would correspond to specific wavelengths. A line spectrum for elements in their gas phase is so distinct that you can use a line spectrum if you're not sure what it is. And based on the colors that you see sort of develop in the line spectrum and also the wavelength that you see, you could actually identify what element you're looking at. So every element, kind of like a fingerprint, has a unique sort of line structure or line spectrum where they have different lines at different wavelengths and different sort of colors in the visible part of the spectrum. And this is the idea here is more of a continuous spectrum. You can see everything coming out at once as we look at it through a prism. Here, though, you see a more quantized version of energy, and we see these distinct lines happening. So just to kind of show you what that looks like here, if we look at hydrogen.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
Now, those 4 lines that you saw for hydrogen are again all a result of electrons in hydrogen jumping from different energy levels. So electrons jumping from higher energy levels to lower energy levels, resulting, say, on the purple line that you saw, or more like the red line or the green line or whatever it may be. Each of those individual ones, again, resulting from an actual transition of electrons. And once again, if we had one that went way down, that's probably going to give us more closer to this end, as that's a lot of energy, which would relate to a smaller wavelength, as opposed to, as I said earlier, if it just kind of transitioned down one, maybe that is the one there. So these 4 lines that we see here in hydrogen is distinct for hydrogen. Not that other elements couldn't have the same colors, but they won't have the same combination of colors and wavelength where all these lines break out. So for hydrogen, this is kind of this distinct pattern of wavelength and colors that you see. Now, this led Bohr to come up with an idea of the spectrum that we see for the hydrogen model, or the Bohr theory for the hydrogen atom. And it's quite complicated, so we're obviously not going to go into great detail about it, but it does explain very well, in a sense, what we see in terms of hydrogen and its emission spectrum, why we see those 4 lines. It does start to fail, as we'll talk a little bit about, as we move away from hydrogen when there's a lot more electrons involved. It doesn't necessarily hold up well for things that have more than one electron, but it does sort of explain nicely, in a sense, what's going on with hydrogen. You may be familiar with the idea of Bohr and maybe not know it's the Bohr idea, but we basically have our positive nucleus here because we have our protons. And the idea of Bohr is sort of this planetary model where we have, badly drawn, but we have these orbits. And we have these orbits where electrons are restricted to be in, and they're going around in pretty little circles, around the nucleus. These orbits have different energy levels. So for example, n equals 1, n equals 2, n equals 3. N is the principal quantum number. And again, that's a fancy way of saying energy levels. So these different energy levels are where electrons are. And sort of in the Bohr model, it was thought that they are restricted to being within those orbits, traveling around in these circles. And what we're seeing in terms of those emission spectrums where we see these different lines coming out is, for example, an electron at a higher energy level maybe working its way back down to a lower energy level. Again, the atom itself would give that off in the form of light. And again, that may correspond to one of those lines that we see. Again, the different sort of transition of electrons from different energy levels. And this is the idea, again, nucleus. and we have our kind of energy levels, n equals 1, n equals 2, and so forth. And as we will talk about, it doesn't necessarily hold up really well. We do kind of move away from it from hydrogen, but talking about principal quantum number, which is n, it can have a value of 1 through 7 in terms of what a principal quantum number could have. By the way, there's actually 4 quantum numbers. We're not going to talk specifically in great detail about each of these. When you take 1A, you will. But the 4 quantum numbers are n, which is essentially the energy level, like we're talking about here. There's L, which kind of tells you, what is referred to as the orbital, where the electron's kind of at. M sub L tells you basically how many there are, in a sense, some other things of those orbitals. And there's also M sub S, which is the spin quantum number, which is how your electrons are basically spinning. And we'll touch upon a couple of these as we go through the rest of this chapter. But again, not in great detail, just enough to kind of tie it together what we're talking about. But n for sure you do need to know, which is the principal quantum number. When you have an n equals 1, that is the ground state. That is the most stablest sort of state. That's the lowest in energy. That is the one that is closest to the nucleus. Anything above that, kind of like n2 through 7, those are what are referred to as excited states. And those are higher in energy. They're also further away from the nucleus as well. And these are, again, sort of levels within the atom as to where we would find an atom, kind of flying around. And as we saw before there, again, a much larger transition of energy being given off by the atom, a smaller wavelength color in the visible part of the spectrum versus the guy here on the left, which is our red, which is not giving off a big color. So those 4 sort of lines that we see in hydrogen could be accounted again from these transitions of electrons within hydrogen, these common sort of transition of electrons from different energy level. Again, each of them are going to give off a different amount of energy as they transition. And again, that will correspond to a different sort of wavelength. And this is a picture of sort of the difference, again, in the sense of continuous energy versus quantized energy. Again, like the sun and stuff, we have this sort of quantized. You could really end up anywhere along the way here. With our continuous here, you could end up anywhere along the way. With our quantized energy, like we see with atoms in the gas phase, you got to be there like our stairs. So again, you got to be on one level or the other. You will never find, again, anybody just kind of hanging out in between levels. And again, we could calculate the energy associated with that as well as, using that equation we just used. So the energy associated with that, and obviously our one that involves our wavelength as well, we can use to calculate as those electrons transition from one energy level to the next. There's a much better ramp picture. Again, continuous energy, everybody coming off at once. You got to be here, 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 or here, and quantized energy. And again, the idea there in a quantized energy is they will either gain enough energy or lose enough energy to make the transition fully. And again, it could be one energy level at a time, or it may transition multiple energy levels at a time, either up or down. But regardless, they will always gain enough energy to make those transitions fully in a quantized version. And again, that is basically represented by what you could calculate with that equation, basically. Now, as I mentioned before, electrons really don't sort of travel in these pretty orbits like sort of Bohr's model. And as we get into atoms that have more than one electron, which is pretty much everybody else, it doesn't really hold up very well in terms of its theory and idea. And what happens is we see sort of a move away from Bohr's idea of, I know for sure, if you want to think of it this way, like I know for sure I have my nucleus here, I got my orbits. And you could kind of think of it this way if you want, like in sort of Bohr's model, it's quite predictable, right? If you have something that's traveling around in a circular orbit, there's a good chance you could locate exactly where it is, right? If you just kind of wait there for it to come back around the corner, right? It's going to eventually has to come back around. And that's sort of the idea that he had. And what it turns out to be with some things that we're going to talk about here is they really don't travel that way. So particles really don't travel in these really well-defined sort of ways on these pretty orbits. And they can have sort of a wave-like function as to how they travel. And what we're going to be doing is sort of moving away from this idea of orbits and kind of really for sure knowing how they're traveling to this idea of they're really traveling pretty randomly about, right? And the best that we're going to be talking about here as we kind of transition into what is referred to as the wave mechanical model is this idea of probability. Like, I'm not really sure how it's traveling or where it's at, but I think there should be a really good probability that you should be able to find an electron somewhere in this area of the atom. Again, as we'll talk about, you don't really know how it got there, how it's moving, but there's a good probability there. Rather than sort of the Bohr model where I know for sure it's in this orbit and it should be coming around the turn very shortly, there's a more sort of prediction there. So one of the first things that helped us sort of move away from Bohr's model was something done by a guy named de Broglie. He actually didn't do any experiments. He just sort of theorized about it, and later experiments actually showed that he was right. And he basically thought about the idea that the electron in the Bohr atom was restricted to orbiting the nucleus at these fixed distances, right? So if it's in an orbit like a ring around it, it's got to be just located exactly at the same distance, right? Pretty much the ring is from the nucleus. And for decades, no one could really understand why that was. But what de Broglie sort of reasoned was this idea that light can behave like a stream of particles, like photons, and particles could also have wave-like properties. So electrons, which is a particle, could have a wave-like function. And according to de Broglie, electron is bound to the nucleus like a standing wave. So obviously, as we talked about, the nucleus is positively charged. Electrons are negatively charged, so there is going to be an attraction between them. If you think about a standing wave like a guitar string, right? Your guitar string is, most cases, tied down to the guitar, right? But if you pluck it, you do get what is referred to as a standing wave, right? If you look at the string, you'll see a wave basically occur in that case. It can't leave the guitar because it's kind of attached to the guitar. And that's sort of the same idea as what he envisioned with an electron. So even though it's a particle, it's maybe not moving these nice fixed distances, but there is some type of wave function that's going to kind of tie it to basically the nucleus, which explains as well why, for example, the electrons just don't all fly away, right? You can't really take your guitar string and have it fly off the guitar unless you really detached it. But because it's sort of attached to the guitar, it can't really go that far away. Now, he also talked about some ideas of a wave and just some terminology sometimes you hear about. There is a part which are known as a node, and a node is usually the part where there's really no amplitude. And amplitude, again, is usually the kind of peak of the wave there, the distance. And those nodes are parts where there's really kind of no wave function sort of happening at that moment. So basically what he concluded was that waves can behave like particles, but particles like electrons could also have some wave function. And this really moved us in the idea away from Bohr's model, or starting to move away from Bohr's model, to this idea of wave mechanics, where we're like, I don't know, it's somewhere there in that atom. Not really sure exactly at any moment exactly where it's at. And there's some uncertainty sort of associated with it. The next really major sort of step forward in that idea of sort of uncertainty is the Heisenberg uncertainty principle. And basically, the Heisenberg uncertainty principle essentially says that it's impossible to know at the same time how a particle, for example, like an electron, is moving and its actual position. And the idea with the uncertainty part of it is really the more you know about one thing, the less you know about the others. So, for example, the more you know about the position of a particle, the less you know about how it's actually traveling, and vice versa. The more you know about how something like an electron is traveling, the less you know about its exact position. And again, this is very different than sort of the Bohr's idea of it's in an orbit at a fixed distance from the nucleus and it's traveling these pretty circles around the nucleus. So again, we have this uncertainty. And really the last thing that sort of moved us away from, again, Bohr's model is this idea from Schrodinger and his equations. And we're definitely not going to get into any of that too much here. If you ever take physical chemistry, it's like the first semester. It's basically a bunch of calculus. So it's a bunch of math and probabilities sort of calculations. And that's really what we're talking about here is this idea of wave mechanics of, again, probability of finding a particle like an electron at some place within the atom. So with that being said, we actually move away from the idea of orbit to these electrons being in what are known as orbitals. And they're sometimes referred to as atomic orbitals. And there's like 4 types of atomic orbitals that we typically talk about. And that is s orbitals, p orbitals, d orbitals, and f orbitals. So these are the different types of really probability maps within an atom of where you could find an electron. Again, the idea here is we don't really know where it's at. It's just kind of moving around. And where's it moving around? It's really moving around in that empty space within the atom, right? That electron cloud outside of the nucleus. We also know that it does have obviously some attachment to the nucleus. It's got to have some attraction that kind of keeps it there. But how it's actually moving around is, again, a more random bit than we do see with sort of the Bohr model. Any questions on that so far? And here's actually a picture of a probability map. And again, you could kind of think of the nucleus in the center if you want. And you can see the differences in color. So the darker color is a higher probability of finding an electron in that area. And as you sort of fan out this way, again, you can kind of see it gets lighter. And that doesn't mean you won't find an electron out there. It just means that the probability of finding an electron is a lot lower than it is, obviously, near the nucleus, right? Because the nucleus, again, being positively charged, there's a pretty high probability that you could find an electron near the nucleus. That absolutely means with what we're talking about is, even though there's a really high probability of finding an electron there, still not really sure exactly where it's at any moment and not sure exactly where it's traveling. But, you know, there's a higher chance of finding an electron there than it is, say, out here. You could still obviously find an electron out there, and the same rules apply. You still don't really know exactly where it is or where it's at. So again, if you were standing here, it doesn't necessarily mean that, you know, that electron would go right at your spot and may come by you at some point. Not really sure exactly where it's coming from or anything like that, but a good chance you would probably perhaps get a vision of it if you could. So let's talk a little bit about these atomic orbitals and sort of the differences between them. So the first type of atomic orbital is an s orbital. And an s orbital is really a sphere. And the s orbitals actually start on the n equals 1 level. So on the very first energy level is where we see s orbitals. And they will actually be on every energy level after that. So you will find an s orbital on the first energy level, and you'll find it on every single one after it. So for example, if this is our energy level here, increasing this way, on the first energy level, we will find what is referred to as a 1s orbital, the 1 being the energy level, the s is the orbital. On the second, we will have a 2s orbital. On the third, a 3s orbital, and so forth as you continue on. So on every single energy level, starting with the first one, you will find an s orbital. Now, when we talk about orbitals, any individual orbital could hold a maximum of 2 electrons. So no matter what type of orbital it is, no matter what energy level it is, if you have one individual orbital, it can only hold a maximum of 2 electrons. The size does get larger as you go from one energy level to next to sort of accommodate all the electrons, but they're all basically the same shape. That means if I wanted to max out in terms of electrons of any s orbital on any level, that's going to be a maximum of 2 electrons, right? 2 in each of the individual orbitals. I could basically put 2 electrons here. I could basically put 2 electrons here and so forth along the way. Does it mean I need to always fill it up with 2 electrons? The answer is no. You could have 2 electrons, 1 electron, or no electrons in an orbital. It doesn't necessarily have to be filled up, but it can hold a maximum of 2. And here's what an S looks like.
An s orbital has a spherical shape with the nucleus at the center.
And again, all these orbitals are basically sort of described as X, Y, and Z in sort of three-dimensional space, like in math on a Cartesian plane there. And here again is our density map versus our size. And as you can see, as we increase, this is basically an s orbital on the first energy level, second and third. Our n equals 1, 2, and 3 in this case. The next type of orbitals that we come across in an atom are actually the p orbitals. And the p orbitals actually start on the n equals 2 level. So that is the first place where we start to actually see p orbitals appear. So if we were to kind of draw our little diagram here, we have on the first energy level a 1s orbital. On the second energy level, we still have an s orbital. That again is referred to as a 2s orbital. That 2 in front means it's on the second energy level. And this is where we first start to actually see p orbitals. And there's actually 3 types of p orbitals. There is a px, a py, and a pz orbital. That's basically 3 different orientations in 3-dimensional space. One's on the x-axis, y, and z-axis there. And that's what each of these lines represent. This, for example, is our px orbital or py and our pz orbital. Now, in a case when we have an orbital on an energy level where there are multiples of the same orbital on the same energy level, they are sometimes grouped together. And these are sometimes referred to as a subshell, or depending on your book, a sublevel. So a subshell or sublevel is basically groupings of orbitals together that are the same type of orbital on the same energy level. We do not see that with s because no matter what energy level you're on, there's only one s orbital. So there's not really a grouping of different s orbitals together. Now, we do see this with p, and we'll also talk about d and f. We also see that as well. We see subshells happening there. This is what is sometimes referred to as the 2p subshell. Now, if I were to fill up the 2p subshell, the maximum number of electrons in that subshell is 6 electrons. 1, 2, 3, 4, 5, and 6. 2 in each individual orbital, right? So 2 times 3 is 6 electrons if you filled up the entire p orbitals on a particular energy level. Questions on that there? They are essentially figure 8 looking things like so. It actually has no amplitude there in the middle. That's what's referred to as the node. You could kind of think of it as where the nucleus is. And those sort of lobes are basically probability maps of where you could find an electron. So that is our X.
The 2px orbital is the shape of a figure 8 along the x-axis.
There's our Y.
The 2py orbital is in the shape of a figure 8 along the y-axis.
And then obviously our Z here.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
And again, kind of within those lobes is where you could find a high probability to find electrons. Once again, that kind of being like your nucleus, you could see highest area kind of near it is, again, not sure exactly where it's at, but again, a probability of where you can find those electrons in each of those cases. And the same thing, obviously, here you can see darker areas here and darker areas sort of here as well. Now, the next type of orbitals where we find electrons are actually d orbitals, and d orbitals do not begin until you get to the third energy level. That is where they start, and that is the first time that you see d orbitals. And there's actually 5 different types of d orbitals. And again, if we're drawing our thing, n equals 1, 1s, n equals 2, 2s, 2p. And now if we go to our n equals 3, we have a 3s, 3p, and 1, 2, 3, 4, 5. That is our 3d. Once again here, all 5 of those d orbitals together on the same energy level is known as a subshell. Yeah. So that would be the 3D subshell or sublevel. And if I maxed out that subshell, how many total electrons could I put in there? Could do 10. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. So again, if each arrow is basically an electron, you could put 10 of them in there and max it out. We see d orbitals starting on the third energy level and really going to kind of the sixth energy level in terms of what we use it for. It can go further than that, but we pretty much don't go much past the sixth energy level for our Ds. For our Ps, it starts on 2, and it usually can go to 7. But our Ds, usually we don't go past, again, 6. But you can definitely technically go past 6. But the purpose is we don't really need it for what's on the periodic table, essentially. As you can see there from the picture, essentially they kind of look like two p orbitals together, basically, and stuff. So here's what they look like.
Cloverleaf shape that lies in the xy plane and is aligned along the x and y axes. The 3D x squared minus y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x.
The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y.
The 3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z.
And then we have one here, maybe. Kind of looks like a donut there.
Shaped like a PZ orbital, with a donut of electron density around the center. It is aligned with the z-axis.
So would we see all these shapes in real life? Yeah, probably not, right? These, again, are more of theoretical probability maps of where we could find these based on calculations and stuff like that. The last type of orbitals that we really do deal with are actually the f orbitals, and the f orbitals really do start on the fourth energy level is where they start. There actually is 7 types of f orbital. And that means obviously here, if we have 7 times 2 for each orbital, maximum number of electrons, going to be 14 electrons here. Once again, the F does run from 4 and it can run all the way to 7. But in reality, for what we have on the periodic table, we usually don't go past 5. So on the 5th energy level is kind of where we kind of max out in terms of F orbitals. But you definitely, in theory, can go past that. Again, we just don't really need to do so for what's on the periodic table. So once again, if we were drawing our pictures, we got our 1s, we got our 2s, and our 2p. We got our 3s, 3p, and 2, 3, 4, 5, 3d. We can go up here to try not to run out of room. So n is equal to 4. We have our 4s, our 4p, our 4d, and this is where we first start to see 1, 2, 3, 4, 5, 6. Yeah, squeeze it in there. 7, our 4f. Let's kind of put a line there. Orbitals basically first start to appear. Once again, just like the p, just like the d, all 7 of those 4f orbitals together are what are referred to as the 4f subshell, the grouping of all 7 of those individual orbitals together on the same energy level. Questions on that there? So let's talk a little about the energy of these orbitals. So within the energy of these orbitals, what we do see is in something like hydrogen, where there's only 1 electron, all the energy of these orbitals are exactly the same. And what I mean by that is if you look at these energy levels, this is essentially n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Obviously, there's more, but not listed here. And everybody on the second energy level basically is all equal in energy. Everybody on the third is all equal in energy. When we talk about some terminology, another terminology that we sometimes come across is what is referred to as a shell or a level, depending on whose book you're reading. And when we talk about a shell or a level, we're talking about every single orbital that's basically on a particular energy level, like the n equals 2 level. So we have levels or shells, which is the entire energy level, every orbital, no matter what type it is, that's sitting on that energy level. We have subshells, which are the same orbitals on the same energy level, grouping of them as well. And then we have individual orbitals, which are just one orbital by itself. So for example, if I want to know the maximum number of electrons in a n equals 2 shell, and I also want to know the maximum number of electrons in a 3p subshell, and the maximum number of electrons in a 4d orbital. Take a moment and decide how many electrons can we put in each of those. That is everybody. So I could go 1, 2, 3, 4, 5, 6, 7, and 8 electrons if I maximally filled up everybody on that level. Doesn't mean you need to fill up everybody on the level, but if you maxed it out, that would be your max there. How about for the 3p subshell? How many electrons can I put in that one? It is 6. The 3p subshell is that grouping of those p orbitals together. And that would be 1, 2, 3, 4, 5, and 6 electrons. How about how many electrons in a 4d orbital? That is 2 electrons, by the way. So any individual orbital could be that one, could be that one, could be that one, could be that one, or that one, could only hold a maximum of 2. So that's usually a trick question sometimes people ask. So if they ask you how many electrons in just an orbital by itself, regardless if it's a 3d orbital, a 4p orbital, a 2s orbital, it's going to be 2. If I want to know how many electrons in the 4d subshell, how many would that be? 4d subshell would be everybody there, right? So that would be 10 electrons if I did the 4d subshell altogether. Any questions on that sort of distinction between names sometimes? No? Now, you may not want to, for example, if you had a question where you wanted to calculate how many electrons there are on a particular shell or level, you might not want to draw all this out. I don't blame you. So there's actually a calculation you could do if you want to know the maximum number of electrons on a shell or level. You take 2 times n squared. N is that principal quantum number. That's these numbers here. So to show you how that works, if we take the n equals 2, 1 like we did, you would do 2 squared, and you do want to square it first and then times it by 2. So that's 4 times 2 is 8, which is again what we got here, right? Now, if I did the third energy level, if I did this guy, which encompasses everybody, that would be 3 squared times 2. That is 9 times 2 is 18 electrons. And again, that is 1, 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons if I filled everybody up on that particular energy level. So again, you do want to square first the n number and then times it by 2, not the other way around. So that's a good way, get into n equals 5, n equals 6, n equals 7. You don't want to really calculate or draw it out or try to draw it out and stuff like that. Now, if you took a look at, say, n equals 4, for example, right? And you did that, that is 4 squared times 2. That's going to give you 32 electrons, right? Now, if you go n is equal to 5, that I believe is 5 squared times 2. That's going to give you 50 electrons. Now, you may be asking yourself, if we stop at f's, right? Shouldn't it be kind of the same number of electrons as you continuously up the ante there, go to the next energy level and stuff like that? So the short answer is there actually are other orbitals besides F. They actually go alphabetical after F. It's like G's next and so forth. So just kind of go alphabetical after that. The reason we don't usually talk about that is We usually don't need it. So everybody on the periodic table pretty much would be covered, like I said earlier, by getting to the F. Really, the 5F will cover everybody who's on the periodic table. So we don't really get into those because we don't need it for anybody on the periodic table. But just to show you, and again, this is the only place we're going to talk a little bit about those quantum numbers we talked about before. And maybe they answer the question of, let's get rid of some of this marking here, I think. Where's that? There we go. To answer maybe a question you might have, like, why on the first energy level, for example, is there only like s orbitals and stuff like that? It's really explained by the quantum numbers. And if we do n, which can have a value of 1 through 7, the other quantum number, which is L basically tells you the type of orbital you're dealing with. So L could be 0 to n minus 1, and those are acceptable values for L, for example. So if we did it for our first energy level, if n is equal to 1, L could be 0, and it could go to n minus 1. So 1 minus 1 is 0, right? So that's the only number you're going to get. And when you have an L value of 0, what that really represents is an s orbital. And that pretty much tells us that on the first energy level, the only orbitals that is possible to be based on quantum numbers, it's just the s orbital. So that's why there's just one type of orbital there. And how many orbitals are there? That's actually this sort of number, the third quantum number. It could be minus L to 0 to positive L. So for example, minus L in this case is 0, plus L is 0. So the only thing it could be for this guy is 0, which basically tells me there's just one orbital present at this point. And that's again where quantum numbers basically tells us why we have these orbitals and sort of where they're at. And again, you're not going to be responsible to do any of these numbers and stuff like that. Just use it to illustrate why we have these orbitals present. So if we just went to n equals 2, for example, we can have an L value of 0 and also n minus 1, which would be 2 minus 1 is which number? 2 minus 1 is 1, yeah? And we saw that an L value is S. When you get an L value of 1, that's going to represent a p orbitals present. And that's what we see here when we get to the second energy level. We see s orbitals and p orbitals present based on the quantum numbers. And just again to show you why there are 3 of these, if you took the 1 here for L, it could be for m sub L minus 1, 0, and plus 1. That is 3 numbers. Each of those represent like the px orbital, the py orbital, and the pz orbital. So that's why we know, for example, on the second energy level, we should have s orbitals and p orbitals. We also know that we should only have one s orbital there, and thus we get 3 p orbitals. And it's really based on this quantum numbers, which obviously we don't do in here. You will do it in 1A. But that's really the basis for why we have these different orbitals and how many we have and how many end up on different energy levels. So to tie this into what I was doing on this page, the difference between this energy level, right, and this energy level in terms of electrons is about 18 electrons, right? And that would mean that I would need about 9 more orbitals available to me. And if I did my n is equal to 5, my L could have values of 0, 1, 2, 3, and 5 minus 1 is 4. So an L value of 0, as we've been talking about, is an s orbital. An L value of 1 is a p orbital. You get an L value of 2, it is a d orbital. An L value of 3 is an f orbital. And that's usually where we run out. And as I said before, now we actually have an L value of 4, and that again would be technically like your g orbital, if you will. And we could also then drop to our m sub L, which would take us from whole numbers, minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, and plus 4. Each of these would represent one of those g orbitals, and there's 9 numbers. 9 times 2 is the 18 electron difference between the 4th energy level and the 5th energy level. And we never ever touch those because, again, we don't need it for anybody on the periodic table, so we don't see those. So again, when you do that calculation, you're wondering where those kind of extra electrons come from. They come from these orbitals that really are not in use for anything that we need it for, but they are technically available to atoms based on sort of the math part of it and the calculation part of it. They're available there. They're just not being used for anything that we know of. Down the road, somebody finds something that would need that many electrons, that's where they would then populate. Any questions on that? Again, you will not have to calculate anything like the L value, the M sub L value, or any of that type of stuff, just to hopefully explain to you sort of where all those kind of numbers and stuff come from. Any questions on that there? Okay. Now, back to this idea of what we were talking about in terms of energy. As we can see here with hydrogen and one electron, all the orbitals are exactly the same in terms of energy. Now, when we get more electrons involved, obviously that's a problem in a sense because electrons are negatively charged. So when you get a bunch of electrons near each other, do they really want to be near each other? They don't, because they're all negatively charged, which means they ultimately want to repel one another. So what happens is when we get multiple electrons involved, there's actually a shift in the energy levels of these different orbitals. And that affects how electrons go into the atom. When we write something like electron configuration, we write it based on filling order, and electrons go into the atom lowest energy first, and then work their way up. So they try to fill everything low first, and they go to next lowest, until basically they distribute all their electrons. So we would go here first, as that's the lowest, that's the next lowest. We would go here, here, here. And right around here is where the change that most people screw up on. After the 3p, actually the 4s orbitals are lower in energy than the 3d orbitals. And that means that the electrons will go into the 4s orbitals first, followed by the 3d. And that pattern actually repeats. The 5s is lower than the 4d. So they don't fill the atom in terms of electrons sort of perfectly based on the numbers. And when you write electron configuration, we don't put all the 3s together and then all the 4s and stuff like that. I will say, and I'll maybe mention a little bit later as well, sometimes you will see it written like that. And that's usually based off of energy rather than filling order. And pretty much all chemistry classes that you take, including this one, you should always write the electron configuration based on how they go into the atom filling order and not based on energy. I think in all the years, I only had one class that they did it the other way based on energy. So usually in all classes, filling order, which is this order we're talking about. So how is that filling order achieved? This is really the order at which electrons go into the atom. If you know this, and you know what we talked about, that if you filled a s orbital, 2 maximum electrons, filled the p subshell 6, filled the d subshell 10, and filled the f subshell 14 electrons maximum. You should be able to write any electron configuration that you would want. How this works is we always start up here on top, and we basically just continue on, and then when we get to the end, we zigzag back, and we continue on, zigzag back. Then we keep going, we zigzag back, and you can see 3p, then to the 4s, yeah? And then we zigzag back to the 3d. So again, that gives you sort of the correct orientation. Now, you won't have this with you, but this is something that you can really recreate yourself on the paper pretty easily. And all you have to remember is 1, 2, 3, 4, what we talked about. And what I mean by that is we talked about that on the very first energy level, we only have s orbital, right? Not until we get to the second energy level that we first start to see p orbitals. So you go down to the right a little bit and put a 2p. Not to the third energy level that we see d orbitals. Down to the right a little bit, put 3d. Not to the fourth energy level that we see f's. At this point, all you have to do is fill in the numbers to 7 if you want. It don't really matter. You can fill them all into 7. It'll be all right. So you just go 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d. Even if you went 7, it's okay. You're not going to get there anyways, but you don't have to. 4f, 5f. You've now just recreated that pretty quickly and easily. that you'll always have, once again, the right order. So that's a good way to remember how to sort of do that. Basically just start with the energy level that each of those orbitals start on, kind of put it diagonal, and then just put the numbers underneath it, and you'll be good to go. Any questions on how to do that there? All right, so this is leading into obviously electron configuration, and that is the order there. So let's talk a little about electron configuration and what we use it for. So electron configuration, as I said, we write based on filling order. It gives us basically the location of where we can find all the electrons in the atom, what energy levels they're at. When we're writing the electron configuration for something that is neutral, that means it has the same number of protons as it does electrons, right? That's how it becomes neutral. So if we know the atomic number, we should also know the number of electrons that it has. So that's really helpful as well. So let's take a look at here. Here's our little guy. And once again, we're going to always start up there on top. Stop there. So we might as well start here, and then we obviously are going to hit that one first. So let's just start with the first one, which is hydrogen. So hydrogen starting there would give us 1s1 is the electron configuration for hydrogen. The very first one is the principal quantum number. That is that n number. The s is the orbital, our subshell the electron is hanging out in, and the superscript up on top is the number of electrons in that orbital, our subshell. And that is the way you should write it. 1s1, regular size number, lowercase letter, superscript up on top number for the number of electrons. By the way, when you write electron configuration, no dashes, no commas, no crazy things people like to do. Yeah, so you want to make sure you write it that way. That is the electron configuration, again, for hydrogen 1s1. We could also draw what is sometimes referred to as the orbital diagram. And with the orbital diagram, what we use is either lines or boxes to represent the orbitals. And we also use arrows to represent the electrons. So I'm just going to use lines. So in this case, for hydrogen, if we were going to draw the orbital diagram, I'm just going to use a line. And again, you can use a box and label it as a 1s orbital. And when the first electron goes in, it actually goes in the upwards position. And pointing upwards is our 1 electron. And as we'll talk about here in a second, electrons do have spin, and that's actually the fourth quantum number, which is the spin quantum number. They can have a positive half a spin, which is what that is. They could also head in the other direction, which is a negative half a spin as well. Any questions on that there? All right, then let's talk about what happens next, which is hydrogen and goes to helium. And that brings us up to an important rule in terms of how electrons basically go into an orbital. So the Pauli exclusion rule basically says that no two electrons in the same orbital could have the exact same 4 quantum numbers. So they cannot have those quantum numbers we've sort of been talking about. They cannot have the exact same 4 ones if they are in the same orbital. So what that means is if we take a look at our 1s orbital here, and we already, if I drew it as a box, we already have 1 electron in there. By the way, we could only put how many more electrons in that orbital? Just 1, right? Otherwise, we'll be up to 2 at that point. So 2 will max us out. Now, we have very 2 options as to how we could do it. We could either put the electrons heading in the same direction, or we can put the electrons 1 in, up, and 1 down. So just again, to look at quantum numbers, just to illustrate what it is talking about here. If you were to take this electron here pointing upwards in this 1s orbital, that's a 1s orbital, and you were to write the sort of 4 quantum numbers for that, The n value would be 1 since it's on the first energy level. The L value, as we talked about, would be 0 since it's an s orbital. So again, that's basically an s orbital. The m sub L would also be 0. There's only one s orbital there. And the m sub s, which is the spin quantum number, would actually be plus 1/2. And when it's pointing up, the spin quantum number is plus 1/2 in this case. Now, if I did the quantum numbers for my electron pointing in the exact same orbital, in the exact same direction, I will essentially end up with the exact same 4 quantum numbers. That is technically a violation of Pauli's exclusion rule, which says no 2 electrons could have the same 4 quantum numbers. So when we have multiple 2 electrons in an orbital, the same orbital, they cannot be heading in the same direction, otherwise they will violate the 4 quantum numbers. To show you how it's different between it this way, if I took this electron, that is basically the same setup. We're going to end up with the same numbers. But now when I take this electron, n would equal 1, L would equal 0 as its s. M sub L will also equal 0. You may be saying to yourself, that does look quite similar, and it does because it's hanging out in the same orbital. The difference here, though, is the other one is spinning in the opposite direction. And the m sub s for that guy would actually be minus 1/2. That slight difference in how each of those electrons are spinning gives them different quantum numbers. They don't have the same 4 in each case. And that does not violate Pauli's exclusion rule. So what that allows you to do is have electrons in the same orbital that will not violate this rule. And by the way, the first one always goes upwards. The second one always goes down when it goes in the same orbital. And this is what is sometimes referred to as paired spin. Basically, they cancel each other out. You got like a plus 1/2, minus 1/2 in terms of the spin. They'll kind of cancel each other out, and that's what's referred to as having paired spin when you have 2 electrons in the same orbital heading obviously in opposite directions. Any questions on that? So that is sort of the reason why when we get to, say, our next one, which is helium, number 2, once again, we're going to start up here. And we're going to come to this guy, and that's all we need on this case. And that will get us here for helium 1s2 in this case. And again, if we were drawing our orbital diagram, we'll have a 1s orbital, first electron up, second electron down at this point. At this point, we cannot put any more electrons in there, right? We will have to continue on our path to our next lowest energy level, our orbital. And that would mean that we would be zigzagging back here, and we will now have to come to our 2s orbital in this particular case. And that happens over here with our friend lithium. And lithium is 3 electrons, has 3 protons, 3 electrons. Once again, starting at the top here, that's going to give us 2 electrons zigzagging back. That is where we're going to have to put our 3rd electron in. And that's going to get us here in terms of our electron configuration, 1s2, 2s1 in this case. Yeah. By the way, again, the numbers in front, the 1 and the 2, these numbers represent the energy levels. So that is the n equals 2 level and the n equals 1 level. In this case, how many electrons are in the second energy level? 1. How many electrons are in this first energy level? 2. Yeah, so we got 2 electrons on a lower energy level closer to the nucleus, and now we have 1 on a little higher energy level further away from the nucleus. If we were going to write our orbital diagram, and to be truthfully honest with you, if you were going to do this correctly based on energy, you should really draw your boxes or lines kind of like this. But just to save space so I don't run off at the top of the page, I'm just going to do it side by side. So we would have a 1s and a 2s, but again, energy-wise, that's really the right way to do it. We will go up and down, and then up in this case. At this point, we can put how many more electrons into that 2s orbital? We could go 1 more, right, until it's filled. So let's continue on. That's beryllium where that happens. Now with beryllium, we have 4 electrons. Once again, we're starting here. That's going to give us 2. We're going to zigzag back. That's going to give us our other 2 that we need for our total of 4 electrons. And that's going to give us 1s2, 2s2 in this case. And now for our orbital diagram for beryllium, we will need a box or a line for our 1s and one for our 2s. Again, driven by energy, should go upwards, up, and down in this case. We're obviously at this point full in terms of our 2s. We also now have 2 electrons on the second energy level and 2 electrons on the first energy level, basically in this case. We will now, as we can see, have to come back, and now we're going to get into our p subshell, our 2p subshell, which could hold a maximum of 6 electrons. So let's continue on with that. That's going to get us to boron, I think. And boron has 5, which once again here, as I mentioned, we will start here. 2, zigzag back, 4, and into here for our 5th electron. And that would get us 1s2, 2s2, 2p1 in this case. How many electrons are in the second energy level? How many electrons are in the second? It is, yeah. There's actually that second and that is second. So there are actually 3 electrons there on the second energy level. We have 2 in the s orbital on that second energy level and 1 electron hanging out in the p subshell on that energy level. And we still have our 2 here on our first energy level. So that would be 3 electrons and 2. By the way, if you count up the top numbers, that also gives you the total number of electrons that you put in there, which would be 5 in this case. So if you count the top numbers, that'll get you your total number of electrons. In this case, if we draw our orbital diagram, again, not energy correct here, we would have our 1s, we would have our 2s. Remember that the 2p is a subshell that contains 3 individual orbitals. Again, basically our px, py, and pz orbital. So this would go up, down, and when we fill this sort of subshell, we always go left to right, and we start again with it pointing in the upwards direction. Any questions on that there? Now, this also brings us to another important sort of rule when we start getting into these subshells that have multiple sort of orbitals present, and that's what's known as Hund's rule. And Hund's rule basically says that the most stable state for an atom is one where we sort of maximize parallel spins. So if we were just looking at our 2p subshell in this case, and we already have an electron here, we have a couple of options as to where we could put the electron. We could, for example, pair it off. We could also, for example, go next door. Now, as we talked about before, this is what is known as paired spin. When they're heading in the same direction, this is what is known as parallel spin. And according to Hund's rule, we want to go whichever way will maximize the parallel spin. So we don't want to pair off right away. So when you have subshells where you have multiple orbitals, they are always filled like so. You always go one at a time pointing in the upwards direction until you have no other options. That's going to maximize your parallel spin. Then you come back and you pair them off, which you might have seen me kind of put them in that way. And again, they do go in one at a time to the end. Then you flip it around and pair it off. So with that being said, if we got to carbon next, I think. Carbon is 6. Once again, starting here. Going to give us our 2, our 4. Now we could get into our 6 electrons here. So we got 1s2, 2s2, 2p2. Once again, no dashes, no commas, no weird things written. That is our electron configuration. If you count up the top, that's 2, 4, and 6 electrons basically put in. So you just count those guys. We have at this point 4 electrons on our second energy level and 2 electrons on our first. As we know, since they only have an s orbital on the first, you can only always have 2 on the first energy level. In terms of our diagram here, we again would have a 1s, a 2s, and 1, 2, 3, a 2p. So up, down, up, down, up, and again, we're going to go one at a time here to maximize our parallel spins. Any questions on that there? All right, I think we'll lay it up there for today.